In the second part of this presentation, we'll look at some examples of representing AC voltage and current sources by complex numbers and how we can use this to add supplies together to be a single equivalent supply. So suppose that we are given three different components that have voltages V1, V2, and V3, and they are not necessarily in phase with one another. So the first one has a phase angle of 0, the second one has a phase angle of positive 90, and the third one has a phase angle of negative 90. So these are components, and that's why it's a block instead of like a resistor, a capacitor, inductor. So we don't actually know what's in there. We just know that there is something that is producing these particular sinusoidal varying voltages, and they are connected to an AC source. And so based on that AC source, they are getting these particular voltages. And our goal is to figure out what is the value for this source. So Kirchhoff's voltage law is still satisfied. So it has to be that if I add these three voltages together, it's going to give me the source. Now before I try to add them together, I want to write them in phasor notation. So I know that for the first voltage supply, the amplitude is the square root of 2 times 16. So the RMS value would be the amplitude divided by the square root of 2. So for the very first one, the RMS value would be 16, and because there's a square root of 2 in front of all of these, the second one would be 24, and the third one would be 15. So that means that I can write the three sinusoidal varying voltages in phasor notation as 16 with a phase angle of 0, 24 with a phase angle of 90, and 15 with a phase angle of minus 90. Now, according to Kirchhoff's voltage law, I should be able to add these together. In order to add them together, of course, I would rather have them in their rectangular form instead of the polar form. Phase angle of 0 means that I only have a real part. Phase angle of 90 means I have only an imaginary part that's positive. And a phase angle of negative 90 means that I only have an imaginary part that's negative. So I can determine the voltage of the source by adding the voltages together according to Kirchhoff's voltage law. I have a drop, another drop, and then a rise. So if I add those values together in rectangular form in terms of complex numbers, I end up getting that the real part adding these together is 16, and the imaginary part, 24 minus 15, is a positive 9. I'd like to put this back into polar form, and so I can figure out the root mean square value, which is just the square root of 16 squared plus 9 squared, and it's going to give me 18.4. And I can figure out what the angle is, which is just the tangent inverse of 9 over 16, which is going to be 29.4. So in order to write the voltage supply in terms of the sinusoidal varying function, I need to figure out what the amplitude is. And I figured out the RMS value because that was my polar notation, so I would need to multiply that by the square root of 2. And so I can write the sinusoidal source as being the square root of 2 times 18.4 times sine omega t with a phase angle of 29.4. So if I add these three sine functions together, it's equivalent to a single sine function oscillating at the same frequency with a phase shift of 29.4. So this was much easier than trying to use trig identities and bring everything together. So we basically are just treating these as complex numbers for analysis purposes. All right, here's another one where I have three current sources. Notice again that all these current sources in their sinusoidal form or their time domain have been written in terms of the square root of 2 times some number. So it's pretty easy to figure out what the RMS value is for all of these currents, or the effective values. I should probably mention this. So RMS value, root mean square value, is the same thing as the effective value. The one thing that you do need to be a little careful of in this question is looking at the unit. So I have milliamps, and then I have amps, and then I have milliamps. So the reason this number is so different than the other two is based on the fact that they have different units. When I look at my picture again, I have these boxes. I don't know what's in these boxes. Maybe it's a combination of a resistor and a capacitor, or maybe it's just a capacitor or just a resistor. At this point, I don't know. But I do know that the current that's entering each one of these came from this total current that was entering this junction. So the current entering has to equal the current exiting. So I total should be equal to I1 plus I2 plus I3. So my first thing that I need to do is to figure out what the RMS values are, or the effective values. It's just the amplitude divided by the square root of 2. So like I said before, this is going to be 23. I'm going to convert everything into milliamps. So this was 0.29 amps, so that would be 290 milliamps, and then the last one would be 127. So once I have the RMS values, the effective values, I can write each one of those currents in phasor notation. So I have 23 milliamps phase angle of 0, 290 milliamps phase angle of 63, and 170 milliamps with a phase angle of negative 72. In order to use Kirchhoff's current law, I have to add these currents together, and in order to add those currents together, I'm going to have to put them into rectangular form. So I realized that the first current has a phase angle of 0, which means it only has a real part associated with it. The second one has a phase angle of 63, so I can find the real part by taking 290 times cosine of 63, and the imaginary part by taking 290 times sine of 63, and I can put those numbers in. I get specific numbers. And I can do the same thing for the last current, which has a phase angle of negative 72. So 170 times cosine of negative 72 is the real part, and then the imaginary part is 170 times sine of negative 72, and then I get 52.5 for the real part, and then negative 161.7 for the imaginary part. Once I have these in rectangular form, I can add them together. So I can add all these pieces together, and I know that when I add them together, I add the real parts together, right? Those three pieces. So 23 plus 131.7 plus 52.5 is 207.2, and then I add the imaginary pieces together. So 0 plus 258.4 minus 167.7 is 96.7. So I now have the total current in rectangular form in terms of complex numbers. I can convert that back into the polar form. So I can find the magnitude, which is just 207.2 squared plus 96.7 squared, gives me 228.7 milliamps, and I can find the phase angle, which is just the imaginary part over the real part, and we know how to do this with the complex numbers. That gives me 25. So once I have those values, I can figure out what the amplitude of my total current is, because this is the effective value or the root mean square value. So in order to find the amplitude, I have to multiply that value by the square root of 2. And now I can write my total sinusoidal varying current as the amplitude times sine omega t plus the phase angle that I found. So complex numbers are extremely powerful when we're analyzing AC circuits, and we've seen this by just applying Kirchhoff's current law and Kirchhoff's voltage law.